Thanks a lot for inviting me today. I really appreciate it. My name is Blake Matheny. I'm the VP of Engineering at Tumblr. The only shameless promotion you'll see during this is our jobs page. If you're interested in Scala development, we're in New York. So today's talk is largely about things that have failed in the year and a half that we've been using Scala as our primary backend development language. I'm going to spend a little bit of time talking about what I call the 7 sins of backend development, but a little bit of background on Tumblr. So Tumblr does about 1.5 billion HTTP requests a day. That doesn't include our backend service stack. And for a long time was a large monolithic LAMP app. That worked okay until about 2 years ago, and we started having MySQL fall over. And so we built out a few early back-end applications to support some use cases that PHP wasn't a great fit for. And initially we built out the backends in C, and then after a couple of fun projects like that, we switched over to Scala. So we've been using Scala at Tumblr since mid-2011, and primarily we use Finagle. And there's a talk after this that goes into a bit more detail about what Finagle is. We use it primarily as an alternative to Akka, but we do have some play applications that are developed using Akka as well. So this is an after lunch talk. After lunch talks, usually there's a lot of droopy eyes in the crowd, so I'm going to try something a little bit different today. So for each of the 7 sins of distributed systems, I'm going to show you guys a piece of code or a graph. I'm going to ask you guys, anybody in the audience, to say what they think is probably wrong with it. Some of these are obvious, or maybe to me. Some are a little bit less obvious. The other thing is the code comes from myself, because that it would be unfair to just pick on people on the team. Moses, who's sitting right there. Moses, throw your hand up. And Keith, who's sitting right there. If you want, design critique, you can ask them afterwards. So the 7 sins, we'll go through these individually. Initially, these started off just with sort of like the general problem that I saw in lots of pieces of code, and sort of ended up tying that to, well, I realized it was called anti-patterns, and generally patterns have names. So those names ideally are a little bit memorable. So I tried to stick with things like, you can remember gluttony. It's a little bit harder to remember maybe like factory pattern. So when you're writing your own code, particularly in a server setting, you can think back and be like, am I being a glutton, or am I doing this the right way? All right, so we'll start with lust. I want all the abstractions. So this is a project internally. It's called Redis Cover, and what Redis Cover does is it's a sharding middlware for Redis. So clients connect to it using the normal Redis protocol. It handles things like it has key space knowledge. It knows what backends to use. It can potentially handle like winged migrations, things along those lines. So this is some code from Redis Cover, and it's a lot smaller on this screen, so I'm guessing some folks can't see it, but it says object Twitter to Akka. And what this is doing is it's taking in a Twitter future and handing back a Akka future, or a promise in this case. Anybody want to venture as to what the issue is with this code? So there's a few problems with this. One is there's sort of a general readability issue. Implicits, I prefer explicit implicits, as in ones where you call to Twitter, or things along those lines, as opposed to magic happening and you're not totally sure where that magic's coming from. Outside of that, the performance penalty on this is actually pretty significant. I only included a little bit of this, but as you can imagine, there's the reverse process. This is something that's happening all the time. It's coming in via Finagle because it speaks Redis. It's converting it into Akka futures. It's going out and doing its thing, converting back before it hands it to the client. There's a lot of objects being generated here. The performance is, well, the GC profile for this application is not a generally desirable one. And I mean, part of the problem is, until Scala 2.10, and this is a little better now, you had at least 4 options for, this type of abstraction. You had Scala futures, Akka futures, Java futures, Twitter futures. Who has their own future implementation here? I know there's LinkedIn guys, so maybe they do. All right, here's another one. So there's 5 options. So the problem with this, outside of some performance issues, one is it can lead to really hard to spot bugs. And the primary driver for those bugs is there are really dramatic semantic differences between the implementations in terms of what things mean. So one of the most common ones that I see in our code base, because we use Twitter futures, are Twitter's future implementation provides an on success and a on failure. The problem is the type signature for that returns a unit. So people generally think on failure, okay, this is how I'll hook into like an exception that's been thrown and I'll recover that. That is not what it's for. It's for knowing that there was a failure and potentially logging it or incrementing a stat counter or something along those lines. But these are things that end up being pretty different between implementations. You have different language, and then in some cases, the same named methods and slightly different implementations. So this is one issue that's hopefully not going to be in our code base forever. All right, so we have another application called Buster. What Buster provides are note counts. So if you're in your Tumblr dashboard and you're looking at a post and you see the little number for how many people have reblogged it, liked it, things along those lines, that's a service provided by Buster. And I can't actually show you the code, and you'll see why. I'm going to show you some graphs. So this is a production failure that happened in early January. And what you can see here is Buster's happily doing right around 30,000 requests a second in total. And then for some unknown reason, you see this huge increase in errors. So the errors are about 25,000 a second, and successes during that time are about 10,000 a second. So in aggregate, it's doing about 35,000 requests a second. So really, if you were just to look at total requests, it would do something like a big jump up here. So we see this, and then see service latency really increase and get a lot more jittery. It's typically a lot more normalized. And then this is heap, so you can see where we had to restart it. Does anybody want to venture what the issue was here? It's backpressure. So services can handle a finite number of simultaneous requests, even if you have an amazing piece of software that can handle the C10K or C100K problem. At some point, your system should start refusing connections. It's the only way that your backend system is actually going to stay up when something's going on. So in this case, there was no configured, this is the maximum number of requests that I can handle, the maximum number of connections I can handle. So we had enough capacity to handle roughly 33,000 requests a second. When we surpassed that, the system just completely fell over. So this is sort of a question of, would you rather? Would you rather completely fall over? Or would you rather refuse the connection and leave it to the client to retry? So one of the things that's a bit challenging here is this is different for each of these abstractions. So between, if you're building applications with Akka or Finagle in particular, those two, how you configure this is pretty different. And so if you have developers from these different backgrounds, maybe somebody who's really familiar with Akka coming to Finagle or vice versa, they assume things are done a particular way. And when they're not, you see these, nice graphs. So sort of the few things are, applying backpressure is usually pretty easy. Doing a little bit of capacity planning to understand sort of the bounds of your service. But the one thing I'll say is capacity planning, typically what people will do is they'll write a little load generator and they'll throw load at it as fast as they can. And that misses two of the most important things that determine what your throughput will be in production. And that's how slow your clients can be and how slow your backends can be. So most load tests, it's really sort of on my dev box or on the test environment, how quickly can I throw things at you? In reality, in production, you're going to have systems where the client, the load on the box is maybe 70, and it's taking a second for it to actually connect. So if you're going to go through the exercise of a bit of capacity planning, also go through the exercise of writing reasonable load tests for your environment. All right, so this is my code. This is from a system called Oscar. Oscar's a memcache proxy that sort of knows about like shard pools and parses the request. And this code in particular, basically when you fan out and say I need a bunch of values associated with these keys, you get back you can see it here. You get back a sequence of values. And a value is just like a response that was associated with a key. And what I was trying to do here was count for a given key whether there was a hit or not, so that I could expose some stats that was basically like hit ratio, miss ratio, things like that. So I noted also that in this code, making this method fapply is the same as calling future.get. So this one's maybe one of the more obvious ones. What's an issue with this code? Oh, thank goodness. I was like, no one does this but me. Blocking, and this is in like the main event loop. So basically, requests would come in, and before I sent them back to the client, I would do this kind of calculation. So I couldn't find, this is older code, and I couldn't find a graph from that time, but what you'd see is essentially it would do about 24 requests a second. We have about 24 boxes, or cores per machine. So this would just literally block from allowing work to proceed. So instrumentation here was good, but not doing stupid things with your code is also good. And this is one of those cases where all of these abstractions provide methods for dealing with this case. And at this point, I actually did know what they were, and it was hard to do, so I just like cut corners and did this. But use map, use for each, use whatever abstractions available to you. Avoid blocking your event loop. It'll improve your throughput. And I mentioned this already, but you can hook into either a successful or a failed future, at least with Finagle, and Akka has something similar, so that you can basically defer any kind of stats or calculation until after the request has been handled. All right, so sloth, when not to be lazy, and there's a little bit of discussion about one of these issues. These are, the top one is a piece of code. It's from a internal utility library called ServiceUtil that all of our services hook into. And the one below is an exception from a system that's open source called Collins. It's fixed, so don't worry about using it. So the ServiceUtil one, we have this apply method that's part of an object, and basically what it does is, given some client config, do I already have a connection to the backend or not? And if not, create one and put it in this map. And the next one is it says caused by java.lang.exception in initializer error null. It's amazing error logging. Does somebody want to take a guess on either of these? For the top one, there's two sort of bigger issues. One is you can end up with stale connection handles. This is a recipe for a memory leak depending on what ends up in that map. The one that's a little bit of a bigger problem is, depending on how complex your backend service is, shutting it down properly can be non-trivial. So in this case, the process for actually needing to iterate through that map, pull out all of the clients, call the shutdown method on them individually, it does not exist in the code base. So what that means is if you use this method, you're going to end up with either a JVM that won't shut down, or a bunch of connections you're going to end up forcing a close on. And then the last one, that's definitely a class initialization problem. So in this case, it was a LazyVal. And it was something that didn't manifest itself until a particular load was applied against this system, in which case it exposed a subtle bug in our code. But the two big things were, I think Daniel talked a little bit about this morning, there's pros and cons to LazyVal. There's potentially some performance issues. It can end up blocking. But also, I think the thing that's a little bit worse about this is it violates anybody remember what's the principle of getting back an object that hasn't been fully initialized yet? There's a name for it. So if you throw exceptions in your constructor, it's generally somewhat bad practice. And in this case, it's not even an intentional exception. It's one where, you know, it's being thrown on your behalf. So in this case, we moved to using a static initializer, private constructor, so that we could guarantee that things were set up in a particular way. But in this case, you know, sometimes the lazy vals are easy to spot in your testing. Sometimes you run into issues due to deadlock, other things when you're operating in a highly concurrent environment. All right, so this is another project. It's called Wentworth. So if you're ever in your Tumblr dashboard, you'll see these little notices laid into in between posts. So you'll see a post, then you'll see a little notice that'll say, so-and-so followed you, so-and-so reblogged your post. So this is a Redis-backed service that provides those notifications. And so what this code is for is we have generally we expose a thrift interface for this service. So when we get a request that there's been a new notification, the client doesn't actually need acknowledgement for the write. So we queue the request, and then sort of in batches, we write those to disk. So this code, class Redis writer, gets a handle on a Redis client. And then it has a write queue, which might be like a blocking queue or something similar. It extends runnable, has a run method, and then says, while true, drain queue. I simplified the drain queue part, but that's sort of the gist of it. Anybody want to venture as to what the issues are for this one? There's no way to shut it down. So this one certainly isn't a Scala specific thing, but it ties a little bit to how you mix your abstractions. So if you're using something like Akka, maybe you send a poison pill, maybe you send a particular message type, things like that, wait for it to drain. Finagle has sort of similar, you know, facilities, but you know, that's the question. You go through that shutdown process. How do you make sure that all of those messages get written? You stop accepting connections. And all of these abstractions offer slightly different ways of solving that. So this is a subtle bug because unless you're actually tracking messages received and messages written and looking at that delta, you're probably not going to notice because you're getting, you know, millions and millions and millions of these a day, and it's a data loss issue, right? So in this case, notifications, they're not like, I wouldn't say it's like cherished data because we only keep a finite amount of them. But if you can avoid losing data, that's a pretty good practice. So, you know, in this case, yeah, there's no way to shut it down, and there's a few ways to do that, right? So, if this was a pure Java app, you might interrupt it, catch that exception, shut down. If you have Akka available to you, you might send a particular message type. But this is also something that isn't completely trivial, although the cake pattern made me think I was just doing things wrong. You have a bunch of things to shut down, right? So when your process needs to restart, and some people like to use OSGI, you know, reloading. I prefer just treating it like sort of a system process. I think it simplifies a few things, but you have to handle a whole bunch of shutting down. There's stop accepting new connections, drain out your current work queue, wait for your clients to disconnect, disconnect from any backends that you're connected to, and actually finish shutting down. So this is just sort of one example where that small part of it, which is draining your work queue, there's actually no way to do this. This will just keep running forever. And even if this is a daemon thread, it doesn't actually help you a lot because it's entirely possible for the JVM to exit before the queue gets drained. So yes, it means that you probably won't get stuck with a JVM that you have to kill -9, but it does mean you're probably going to lose messages when the JVM exits. So this one I took from Philip Haller emailed me. It was nice enough to send me over a presentation that he'd done on, it was a bit more focused on sort of mixing the different concurrency abstractions, and there's a link to it there. And this was an example that I'm sure we have in our code base. I did not have time to find it, and he already had a good example. So in this case, you have some actor. It has a state variable. When it gets a request, it replies with some future handle request, hooks into the state, and then change state. Says set the state to this new value. What do you think the issue is with this? Yeah, so this is fun with closures in a future. So you actually are going to, whenever this block gets executed, you're going to have a handle on whatever the value of state is at that time, and not the value of state when you actually made the request. So this one's actually fairly easy to fix, potentially, if you wanted to do this. You can just actually bind the value so that within that closure, you have a value that is the one that you actually wanted. You can do fancier things. You can use atomic ref or STM or things like that. But I generally try and not decorate my code. I usually like to do things sort of as simple as possible, as readable as possible, and avoid abstraction if I don't need it. So this is a case where I think people generally sort of have a distaste for vars. They're like, that's a code smell in itself. I definitely fall into that category. There are times when that's a really simple thing to do. It's the thing you're going to use. You just have to be aware of what are the semantics for the abstraction that you're using, and is this thing actually doing what you want or not? The other thing I said is this is a bit of, you can't completely hide from the Java memory model. So we have a lot of, this isn't actually specifically an issue with it, but that's something that I'll run into occasionally, particularly with people using volatiles or things like that, is at some point it's all running on the JVM, and having an awareness of what that looks like is going to help protect you, or at least inform you when you're making decisions about how do I do this stuff, what am I thinking about. All right, so this one's called Pride, Why Mess with Perfection? This is from a system internally called Refrog, and the problem that this is solving is, so we've been keeping these notifications for a short period of time. If we want to keep these for like a year, we need a system that's architected slightly differently. And so there's a feature of this that basically says, and this is something we're rolling out in test mode right now. So this is pretty, I think this is actually still in a pull request. So this is really fresh code. What this is doing is saying, if there is more than 1,000 notifications, or there's more than 3 days in data, purge the data that's older than that. So what this code's doing is saying, it's going to randomly decide to run. Say it's, choosing a random number between 0 and 100, and if it's 1, it's going to run. It gets a count of the number of elements associated with a key. If the number stored is less than the specified count, which is out of scope, it's going to use one method for purging, which is the date-based one. Otherwise, it's going to use the value-based one. And if it shouldn't randomly run, it's going to return a future unit. So there's a couple of problems with this. Does anybody want to venture a guess? All right, so there's a few things. Does this ever run? So there is a probability that that code block will never execute for a given key, right? So yeah, you'd say given enough runs, that probability is very low. But what if a user is really inactive and they end up with one key? Do you just end up sort of never purging any data? So there's no logging, there's no stats, there's no way to actually know whether that case is ever hit. It's just something I can talk about, and it's a thought process. So something else is we have these two different ways of purging data. One is date-based, and one is sort of if a count's been exceeded. It seems like those are good things to know, right? Which of those is happening more often? Is it usually date, meaning that we're not having lots and lots of notifications, or is it usually threshold-based, in which case we're almost never hitting the date one? Without the instrumentation, you're just sort of lost. And then the last thing is the calls to these are Redis calls, zrem range by rank, zrem range by score, and then also the zcount flat map. what if one of those errors? Do we want to log that? Do we want to include it as a stat so that we have better analytics? Part of it is, once something goes to production, yeah, you can always push out new code, but generally you're not just going to say like, oh, hey, let's flip on the instrumentation for this. Like, it's part of what the coding exercise is, right? What are the types of things you need to know about so you can really look at your systems and understand whether they're functioning well or not. So in this case, there's sort of a few things you can do. One is, it's really great if your protocol handler has built-in stats. That's one of the reasons I like Finagle so much, is all the protocols they support, you get more stats instrumentation than you could possibly want. Number of connections, bytes, you get percentiles for all of these values, you get counters. You just get a ton of information. For us, that all submits into a central stat cluster, and we can look at this stuff in pretty close to real time, and it's really helpful for diagnostics. But part of it is actually like doing it, right? If you're not actually collecting the stats, there's nothing to look at. So this isn't particularly a Scala issue, although that's part of the code, but I do think it plays into your choice of which abstraction you decide to use. I personally like the fact that Finagle bundles in their stat stuff. You don't have to use it, but you can. But there's sort of that paradox of choice, right? So the thing that I like about Finagle in particular is you don't have a lot of choices. It's not a particularly fancy framework. You get some stats, you get some futures, you get some protocol support. That's kind of it. There's no like remoting. There's not a lot of support for like serialization. There's no support for actors. They just expect you'll pull that stuff in if you need it from somewhere else. But whether you're using Akka, whether you're using Finagle, sort of doesn't matter. It's, are you thinking about sort of the data you need to collect to effectively diagnose any production issues you might run into. Something that's not covered here, but I think is additionally important, is how do you do your distributed tracing? So there's going to come a point in time where you have or you already do, have a tier of services. So, your front end makes a request to this system that makes parallel requests to this other back end system that makes requests to these other back end systems. And all you know from the front end perspective is that took a really long time. And that's not helpful information. If you've ever gotten a bug report saying it's slow, you know how frustrating that can be. So one of the things that we did is a lot of our code's instrumented using Dapper-style tracing, which basically means you have these notions of span IDs and trace IDs, and those persist throughout the lifetime of all of these requests, so that you can go back and look and say, okay, that took a really long time. Where did it take a really long time? The great thing about that is, because we've also provided instrumentation at the protocol level, we know specifically, like, if it was a back-end storage system, we know which one it was, and we know why it was, and things along those lines. So these are things, if you can do it up front, that's great, and if your abstraction of choice supports it, that's even better. So a few of the things that I've picked up over the last year and a half or so of working on this stuff, I don't think that there's a better or worse for Finagle or Akka or the other systems out there that solve some of these problems. It's just you use the one that makes sense for your environment. I do think you should be really consistent in the application of that, because I've basically seen nothing but problems in trying to mix these together. And that's really just because when you do that, you have these subtle differences, and depending on the knowledge level, whether it's Akka or Finagle or whatever it happens to be, their expertise in it is going to be a variety of levels. And on top of that, the more abstraction you have, the more overhead. Not just performance, but like time to learn that, time to fix bugs, things like that. Void blocking in your futures, and I brought this one up already, but most load and stress tests are useless. They depend on fast clients and fast backends. So if you're going to implement these, account for that. It'll make your life much easier.